Welcome to a demonstration of QuickDepth, a tool in model vision for the rapid depth estimation from magnetic data. QuickDepth applies artificial principles to the estimation of depth, magnetic properties, and geological style from magnetic data. There are many benefits in using QuickDepth in model vision for depth estimation, but most importantly, using the AI component, we can speed up the interpretation process, and it leaves the interpreter in control of the geological interpretation. QuickDepth uses both the line data for the highest possible depth precision and the associated grids to gather intelligence on the shape characteristics of each anomaly. This intelligence is also used to estimate interference from overlapping anomalies to help in the assessment of depth quality or confidence. For this demonstration, I'm going to use a segment from a survey from the Mount Isa region of Queensland, Australia. The original flight line data and grids are available from the Geoscience Australia GADS download facility. This survey was flown over an edge of the Mount Isa province, where the unconformity surface dips to the east, below the Carpentaria Basin sediments. On the left is the total magnetic intensity grid, overlain by the magnetic survey lines, flown with 200-metre line spacing. I'll start by zooming into an area for better viewing in this demonstration. To begin QuickDepth, we need to have a cross-section profile window open. And to do this, I'm going to use the Active Lines toolbar. I just drag it across one of the survey lines that I wish to activate. So to begin QuickDepth, we need to access it from the Tools menu. There are two phases of QuickDepth: the information extraction phase, executed from the Prepare Data submenu, and the depth interpretation phase, executed from the Interpretation submenu of QuickDepth, only after the information extraction phase has been completed. Once the initial phase has been run, the results of this are then available for the current and future sessions once the session has been saved. So I'll click on the Prepare Data submenu. The total magnetic intensity grid is used to derive the 2D estimates of the magnetic tensor, normalized source strength, magnetic field components, total field gradients, and reduction to pole of the total magnetic field. The 3D attributes of the full magnetic tensor carries a lot of shape information, such as elongation, dimensionality, and strike direction. Once the grid processing has been completed, we need to move on to the input line channels. So we're choosing the TMI field in the line data. So we're choosing the micro-leveled channel in this instance. And we're choosing the sensor elevation, or the clearance, which is altitude. And you can see that the upward continuation height has been adjusted based on the grid information. An upward continuation height is applied to the sensor to ensure it is smooth enough to calculate the magnetization. This is recorrected for the depth estimates at the end of the module. We just simply need to process the lines. This completes the information extraction phase of QuickDepth, so we can close the data loading dialog down. Then we can move on to the data interpretation phase. After making a cross-section active, select the Refine Selection in Cross-Section button in the QuickDepth Interpretation dialog. Then use your mouse to select the data range by dragging the mouse across the anomaly. Two vertical dashed lines will indicate the location of the selection. Then select the Compute Depths button, and the dialog fields are filled with the interpretation results for the different estimation methods. The first column shows the depth below ground. The second column is the estimated azimuth direction of the anomaly trend derived from the sensor data. The third column is populated with QuickDepth's best estimation of the body type. The quality estimator field shows values ranging from 57 to 75, with the Peters length showing the highest quality result. This is meant to be a guide only, and if the quality values are all within 10 to 15%, then it is okay to select another method. Below the results table is a line that shows the statistics for the best body type solution. By selecting the Show Full Table button, you can view all possible results for this anomaly grouped by the estimation method. The final solution selected by the user as the best solution has a tick in the best box, and the results summarised in the QuickDepth dialog previously shown are displayed in this table with a tick in the checkbox. Here you can see individual results along with a dimensionality index in the DI column and a structural index in the SI column. The dimensionality index parameter is derived from the tensor with a range of between 0 and 1, where 0 indicates that the magnetic source is linear, like a dike, or line magnetic formation. When the dimensionality index is 1, this indicates that the anomaly is associated with a pipe-like magnetic source. Therefore, the dimensionality index is used to make an initial interpretation of the shape of the source. The structural index is normally defined in terms of poles and dipoles, but these terms have a physical geological equivalent, which QuickDepth utilizes. If the structural index is 1, it indicates that the source is a line of poles equivalent to a thin sheet or magnetic formation. If the structural index is estimated to be 2, the source is indicated to be a point pole equivalent to a narrow vertical pipe. If the structural index is 3, it is a line of dipoles, which can indicate the source might be a sill or a channel fill. If the structural index is 4, it is a point dipole, and it's usually indicating that the magnetic source could be a sphere or an ellipsoid. This table of all results allows the user to compare the results for each depth estimation method and make an informed decision of the best method to be saved in the point dataset. As you interpret each anomaly and save the solution, a symbol representing the top center of the target is displayed in the cross-section view. The depth estimates are reported as points in a dataset called QuickDepth points in Model Vision. After completing the estimate for a single anomaly, you can move on to another anomaly in the same cross-section by repeating the process. It is possible to display multiple cross-sections and continue to analyze the survey. I'm just going to select another line from the map view. Keeping the original line still open, I can then get a feel for what the anomalies are doing across multiple lines. Then I just need to proceed with the QuickDepth interpretation again after the data preparation phase has already been completed and saved within the session. I just refine the selection, compute, and choose my best fit solution. In this case, I'm going to choose the Peters length, and I save the result. After working through the survey lines by cross-section views, it's possible to display the point solutions determined through QuickDepth in a map view and get a feel for the depth estimates of an entire survey area. This slide shows the completed depth estimate for the Mount Isa region survey. The cross sections shown give an indication of the depth variations in the area, and the color modulation of the solutions also indicates the variation in the depth estimate methods that were deemed best fit. The two images shown show the depth values determined by QuickDepth overlain on the TMI image. These depth estimates are saved as points and can be re-imported into Model Vision again as a point data set, which can be gridded, and a depth below ground surface can be computed and then contoured to show possible drilling targets in the area. These depth below ground values can be also exported to an ASCII file to be used in other applications. Thank you for watching this quick demonstration of QuickDepth in Model Vision. For more information on the module, please refer to the Tensor Research website or contact one of our team directly.